What if the ticking of a clock isn't just a measure, but a door? What if the past is not gone, and the future is already written? Asterisk from Einstein's equations to cosmic paradoxes. From rotating black holes to tunnels through spacetime. This is not science fiction. This is the science of time travel, explored, questioned, and calculated. Asterisk. Welcome to the journey through time itself. Time travel. A concept found in ancient myths, scientific equations, and modern physics. Its roots lie deep in the fabric of space and time, and its story unfolds through philosophy, mathematics, and observation. Time, as understood today, is considered the fourth dimension. The first three dimensions, length, width, and height, describe space. Time, when added, forms the structure known as spacetime. In classical mechanics, Isaac Newton proposed absolute time. He described it as uniform and unchanging, flowing at the same rate for all observers, regardless of their motion or location. This view held for centuries. In 1905, Albert Einstein's special theory of relativity redefined time. According to Einstein, time is not absolute but relative, affected by speed and gravity. Einstein's special theory of relativity introduced the idea that time slows down as an object approaches the speed of light. This is known as time dilation. This was experimentally confirmed in 1971 through the Havlicek-Keating experiment. Atomic clocks flown around the Earth on commercial airliners returned with different times compared to identical clocks on the ground. The discrepancy matched predictions from relativity. The effect becomes more pronounced as speed increases. At 90% the speed of light, time for the traveler moves nearly half as fast as time for a stationary observer. General relativity, published in 1915, added another layer. Gravity affects time. Time moves slower near massive objects. This effect is measurable around black holes and in Earth's gravitational field. GPS satellites, orbiting farther from Earth, require adjustments to account for this gravitational time dilation. Relativistic time dilation permits a form of time travel into the future. A person traveling near the speed of light would age more slowly than someone on Earth. This scenario, often referred to as the twin paradox, involves one twin traveling at relativistic speed while the other remains on Earth. Upon return, the traveling twin is younger, a result confirmed by experimental data involving particles called muons. However, such travel requires enormous energy and technological infrastructure, not currently available. Time travel to the past introduces paradoxes and greater complexity. One concept is the closed time-like curve, or CTC, predicted in solutions to Einstein's field equations. These curves allow an object to return to its own past. The Dell metric, discovered by Kurt Dell in 1949, describes a rotating universe where such curves might exist. Another theoretical solution is the Tipler cylinder, proposed by Frank J. Tipler in 1974. It involves an infinitely long, dense rotating cylinder. If spun fast enough, it might allow closed time-like curves. However, the requirement of infinite length renders it physically unrealistic. Traversable wormholes have also been proposed. These hypothetical tunnels connect distant points in spacetime. If one mouth of a wormhole is accelerated to near light speed, and then returned to its original location, time inside the wormhole may differ at both ends. This could, theoretically, allow for backward time travel. The concept is based on work by Kip Thorne and others in the late 20th century. Stabilizing a wormhole would require exotic matter with negative energy density, a substance not confirmed to exist. though the Casimir effect in quantum physics suggests it may be possible. Backward time travel introduces paradoxes. The grandfather paradox poses the question: if one travels back in time and prevents their grandfather from meeting their grandmother, would the time traveler cease to exist? Solutions proposed include the Novikov self-consistency principle, which states that events on a closed time-like curve are self-consistent, meaning actions in the past cannot change the past in a way that leads to contradictions. Another model is the many worlds interpretation, rooted in quantum mechanics. It suggests that actions in the past create a new timeline or universe. Under this view, changes do not affect the original timeline but rather lead. In quantum physics, time behaves differently. While classical mechanics views time as continuous, quantum mechanics introduces probability and uncertainty. Some interpretations allow for retrocausality where future events influence the past. This idea remains controversial and lacks experimental confirmation. The Wheeler-DeWitt equation in quantum gravity removes time as a variable altogether, suggesting that time may be an emergent property, not a fundamental one. Additionally, quantum entanglement challenges classical notions of cause and effect. Experiments have shown correlations between entangled particles that defy local explanation, though this does not allow for time travel or faster-than-light communication. No known experiment has demonstrated macroscopic time travel. All theories allowing backward time travel involve conditions or materials not currently available. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics prevent time travel to the past. According to this idea, quantum effects would destroy any system that could allow a closed time-like curve. In 2009, Hawking conducted a party for time travelers, sending out invitations. Only after the event had taken place, no one arrived. Though humorous, the experiment highlighted the absence of empirical evidence for time travelers. Time travel has been a frequent subject in literature and film. In 1895, H.G. Wells published The Time Machine, introducing the idea of a device that moves through time. In cinema, films like Back to the Future, Interstellar, and Tenet explore different mechanisms and implications of time travel, ranging from relativity to entropy to time inversion. These portrayals often blend fiction with science, offering imaginative interpretations of theoretical principles. Time travel is also considered in cosmology. Some cosmological models suggest the universe may undergo cycles of expansion and contraction. In such models, time could have different properties in different epochs. The arrow of time, the direction in which time flows, is closely tied to entropy, the measure of disorder. As entropy increases, time appears to move forward. The low entropy of the early universe sets the direction of time. If time symmetry exists at a fundamental level, reversing entropy code. In theory, reverse time's arrow. This remains speculative and unproven. Time travel occupies a unique place between theoretical physics and the limits of known reality. Its feasibility remains uncertain. The equations allow for possibilities, but observation and technology have yet to follow. The nature of time, its origin, its flow, and its boundaries continues to challenge and inspire. If you found this video helpful, just like it and share it.